based on the mock. So far, we have discovered creating APIs by importing specifications such as WSDL. We have looked at Ingress and Kubernetes operator API creation, as well as using the visual API designer. Now we will create an asynchronous API using the API creation wizard in the console. So as Acme, I want to provide a real-time multi-channel API where end customers can subscribe to stock updates. So the type of API we'll be creating will be able to mediate over event broker technologies and expose data publication and subscriptions using web technologies like REST and webhooks. Specifically, I can use HTTP GET to perform long and spontaneous polling. I can use HTTP POST to maybe inject data. Maybe in a Kafka topic, I can use server-side events for web streaming and WebSocket for bidirectional streaming. For webhook, API consumers can register in the developer portal and then provide their callback URL to receive messages from the upstream event broker technology. For this particular API, I will give consumers the ability to receive stock updates using WebSockets or webhooks. I will, however, configure the WebSocket entry point to only allow subscription and not publication of messages. So the upstream data source here, the actual stock updates, live in my internal Confluent Kafka cluster. On top of Kafka, Gravity supports RabbitMQ, MQTT, Solace, and also a very friendly mock upstream service to immediately push out messages for debugging purposes. And I will enable the gateway to connect to it using SASL SSL. So with Gravity, I can dynamically configure things like topics doing runtime logic, but in this instance, I will hard code a single shared topic for my consumers. So like previously, I can create revenue generating and restricted plans for my consumers, but in this case, I will allow anonymous access as well as the specific push plan used for webhook consumers in the portal. So everything looks good. So let's go ahead and create this API. With the next generation of our Policy Studio, users can configure flows and apply policies on both request and responses, as well as publish and subscribe phases, where policies can actually execute on individual messages and packets. And this is quite unique and opens up for many interesting use cases. So for the stock API, what I will do is I will create a specific flow just for webhook consumers. So I can add policies to filter messages, normalize with cloud event standards, or integrate with schema registries for serialization and validation. But in this case, I will ensure every streamed message gets converted from JSON in the broker to XML as it receives the webhook callback URLs. Over WebSockets, I'm not going to make any changes, so the WebSocket consumers will still receive JSON messages. Now, as API consumers, we can view async API documentation, we can subscribe to plans. Now, in this case, I will subscribe to a push plan where I will have to configure the callback URL of the server where I want to receive the messages that the gateway picks up from the Confluent Kafka topic. Now, on the top left here, we have the Confluent Cloud Console where we are ready to push messages about stock updates into the topic. In the top right-hand corner, we have a WebSocket consumer client that has established a connection to the gateway for receiving these JSON messages coming from the Kafka topic. And on the bottom, we have a webhook server that listens to the callback URL registered in the developer portal by the application. Now, as we push these messages through, we can see how the WebSocket client received those JSON messages, while the webhook server callback receives the transformed XML messages.
Back in the Gravity console, we can see a bunch of APIs all running on Gravity gateways, sometimes deployed on different sharding tags representing different deployments of gateways, in our case, internal and external gateways. Gravity can also discover, import, publish, and manage APIs running on third-party gateways and brokers. Let's quickly review what it looks like when managing Amazon API Gateway APIs. In my Amazon region, I have one API, a default pet store API, which has an open API specification and some resources. This API is configured to require an API key. There are two usage plans, Silver, which is restricted to 5 calls per day, and Gold, which is unrestricted. Both plans are associated with the pet store API. In Gravity, we've created an integration and deployed an integration agent. This is a container that runs closely to the third party, in this case Amazon Web Services, and can communicate with the Gravity control plane. The agent manages the sync between Amazon and Gravity, including import of APIs and documentation, as well as subscription and API key lifecycle management. Thanks to the agent, we can now discover and import APIs from Amazon into Gravity. We can catalog and publish this API as any other Gravity API, but we can see that the type of API is marked as federated, meaning it does not run on the Gravity gateway. We can see that the Amazon plans are mapped to Gravity plans, and we can still edit things like subscription approvals, which I'm doing here with Silver Plan, allowing applications to subscribe to this plan without approval. Once the API is published, API consumers can now discover APIs deployed across Gravity gateways as well as third-party gateways and brokers. We can see the open API specification that was imported from Amazon. Note that we could have added other documentation pages within Gravity for this API as well, and also associate the API to various categories and labels, enabling API providers to package APIs and events on multiple runtimes into a single entity. We can try the API directly in the portal, but for this API it requires an API key, which we do not yet have. For the purpose of this demo, I will skip the part where I retrieve and use an API key for the Silver plan that does not require a subscription. I will instead jump to the approval flow for getting access to the Gold plan, allowing us unlimited API calls. I'll subscribe to the plan using one of my applications, and taking the hat of the API publisher, I now need to approve or reject this application subscription request to the Gold plan. Of course, this flow can be integrated with custom and third-party approval flows. Now, back as a consumer, my application now has both an API key for a Silver plan and one for a Gold plan. I can now call the Amazon API gateway directly with the URL and API key value retrieved from the Gravity portal, and see how my Gold plan API key allows for an unlimited number of API calls. In addition to managing APIs deployed to Gravity gateways or to third-party gateways like Amazon, Gravity can also discover, import, and manage event APIs running on event brokers like Solace. In Solace, we already have a few event API products, event APIs, and event linked together. I will focus on the example Gravity Solace Stock API event API product. This holds an event API called Stock API and a plan called Gold. In Gravity, we have created a Solace integration and configured and deployed an integration agent that communicates between the Solace event portal and Gravity's control plane. We can see that we have a few event APIs imported, including our Stock API. Beyond importing metadata like version numbers and description from Solace, Gravity also mirrors the OAuth2 Gold plan from Solace as well as the async API documentation. Again, we can augment this documentation with any Gravity documentation page. Once published, API consumers can now discover APIs deployed across Gravity gateways and third-party gateways and brokers like Amazon and Solace. In this shortened demo, I will skip all the possible configurations in Gravity's access management in terms of multi-factor authentication, identity provider federation, logging experience, and complex OAuth2 customization. Instead, we will use an existing, previously configured application to subscribe to the Solace Event API plan. For now, I will just copy the client ID and client secret for this application. Viewing the API, I can browse the async API for the Solace Event API. In this case, the API can be published and subscribed by using MQTT. For this plan, the subscription requires manual validation, so the API publisher needs to approve the request. Once this happens, the Gravity integration agent will be creating the right subscriptions and access groups on the Solace side. Using Postman, I will now retrieve a JOT token from my application, completely managed by Gravity's access management capability. We will then use the MQTT protocol and specify a Solace-specific authentication using my JOT token that was generated for my subscribed application. I will copy the URL from the async API documentation as well as the topic name to subscribe to. Once connected directly to the Solace event broker, I will simulate a message being produced from within the Solace test publisher interface, and I can see how the events are coming through. The Solace event broker is actually validating the incoming JOT token against the Gravity Access Management Gateway. This showed how Gravity can manage the import, publication, subscription management, and the entire access and authorization provisioning for Solace event APIs. With Newt AI comes AI-driven schema detection and generation. For now, I have a simple pet store API where full endpoint logging is enabled on the gateway. We can see that we only have a very limited API documentation for our API, describing just a single path and method, without any descriptions or payload schemas. The API page is configured to fetch the content of the documentation from a GitHub repository managed by the developer or API publisher. We can see that the GitHub repository matches the very limited OpenAPI specification over PetStore API. The same API document is also represented on the developer portal. Now, with Newt AI enabled and full payload logging configured on our API, we will run some automated API calls against the API. These API calls will simulate traffic against PetStore paths and methods, as well as various payload examples that are not yet fully documented by our OpenAPI specification. Newt AI will learn from the API request and the responses provided by the upstream service and use machine learning to create a new version of the API structure, as well as generative AI to create developer-friendly descriptions and examples as part of the specification. The API publisher can now see the changes between the current version of the OpenAPI specification and the version detected and proposed by Newt AI. The API publisher will now review, approve, and merge the proposed changes. The changes can then automatically or manually be fetched from the repository to update the API documentation. A refresh in the developer portal shows the updated API documentation, including descriptions and examples generated by Newt AI's generative AI capability. Let's have a look at a popular approach by customers to technically group multiple APIs into a single bundle or API product. While categories and labels can be used to help consumers navigate and get visibility into API assets with similar attributes, creating an API product helps technically requiring only a single API subscription for accessing multiple APIs. In our case, we have two APIs that proxy AI models through the popular Hugging Face platform. The Weather Forecast RAG API first retrieves user location information and meteorological time information from third-party APIs before generating a prompt to the underlying LLM model. And the Product Feedback API also uses Retrieval Augmented Generation, or RAG, to enhance the prompts. We will explore this API in more detail in a moment. We also created an LLM product bundle that holds both of these APIs. Through flows, plans, and policies, we could achieve individual rate limiting or access control for the different applications for the different APIs, but currently our bundle is simply routing to the two LLM APIs we showed earlier. To represent the product and API relationships as part of our bundle, we can export the LLM product bundle application. Here we can see that both of the APIs are subscribed to this bundle. The end user can now use a single subscription to access both of these APIs through the LLM product bundle. Let's explore the Product Feedback API, which is part of the API product, in more detail. When calling the API, we first point to the product facade and then apply the product feedback path. We're using an API key that will be validated by the product, as well as an authorization token which will be required by the Hugging Face APIs. In our demo, we'll be doing a negative review of a car alarm product. We can see that the underlying LLM API is responding with a summary of the feedback, potential steps to address the concerns from the reviewer, and a perceived rating. Let's see how Gravity helped augment the prompts using this API. It is worth noting that any of the 70+ policies can be applied to OpenAI or LLM API proxies, including caching, rate limiting, whether that's GraphQL or other rate limiting, and calling out to third-party services, which is what we will be doing in this API. First, our API is ensuring that there is a Hugging Face token in the request. Otherwise, our APIs will not be able to communicate with the Hugging Face platform. Next, we will set some internal variables. One for the sentiment model, which will be used to retrieve a third-party sentiment analysis before enriching the prompt. And one for the model, which will be used to retrieve proposed next steps to address the review. Next, we will call out to the third-party API, in this case the Hugging Face API, and the sentiment model, sending the incoming product review in the body and storing the max rating and complete ratings from the response to the different variables. We will then calculate a few other variables, including the final score out of the max score. And next, we will be using these variables to enrich the prompt to the final LLM model. And finally, we will be instructing the API to forward the prompt to the Hugging Face LLM model we stored in the variable in the beginning of this flow. Once we receive a response from the upstream model, we will store it in a simple variable and then finally create a response combining the response from the upstream and the final rating we created earlier.